Okay, next topic we're going to talk about is something else that is important on beams, and that's going to be shear stress. Now, we talked about shear stress earlier. The shear stress we talked about earlier was in the context of direct stress. So when it was in the context of direct stress, we're taking a connection and we're pulling on that connection, and the bolts are going to feel shear. Okay? Those bolts are directly or simply loaded such that they have to develop a shear stress or else they'd rip apart. Okay? So it was almost in response to a I don't want to say an axial load, but you get the idea. It was you had a load either trying to punch through a plate or rip a bolt in half, and that was the shear stress that we talked about. And that was simply load divided by area. Now we're talking about shear stress in the context of beams. Okay? And we just got done talking about bending stress in beams. And bending stress in beams was a little bit more complicated. Shear stress in beams will be a little bit more complicated than it was before. The sort of what I refer to as the exact shear stress formula is a formula that looks like this. And again, I give the stress symbol with a little V next to it for shear. But the exact formula is for shear is VQ divided by IB. All right? Now I want you, before we talk about this formula in depth, I want you to think about what we're talking about. If I had a beam, this picture, but if I had a beam and you're talking about, hey, I've got a shear force acting on the beam, what would the shear stress actually be? Well, the shear stress would be a resistance on a cross section of that beam, and so there'd be tiny little stresses that would occur that if you totaled all those little stresses up, they would counteract that shear force. So, imagine, if you will, I had this big shear force of 50,000 pounds acting down on this section. In order for the beam not to just split in half or rip in half, I'd have to develop shear stresses over this cross-sectional area to be exactly equal to that 50,000 pounds. Okay? So, the concept of stress being an internal resistance that we talked about earlier, even in direct stress, that same concept holds true. It still is this internal resistance. So anyway, but when we deal with beams, it's a slightly more complex formula, VQ over IB, although this really isn't that hard of a formula. What do you think V is? V stands for shear force, right? So it's the shear force that you are subjecting your beam to. It's going to be, in U.S. units, it's going to be in pounds or kips. Where do you think we might find the shear force? If I have a beam and I say, hey, determine for me the maximum shear stress. Well, again, the maximum shear stress is only going to occur where the shear force is maximized. Where would that happen? Or where could I find that out?
Would it be where the load is placed on it?
No, not necessarily. Have we done anything that might tell us what the magnitude of shear is? How about a shear diagram? Okay? So again, just like bending stress, you might take the bending moment off the bending moment diagram. With this formula, the shear force very well could be taken off the shear diagram. Okay, Q. Q is called the static moment of area. I'm going to come back to that one because this might be the most complicated part of this formula. Okay? I is just a moment of inertia. Okay, same moment of inertia that we'd be using in our bending stress formula. Okay, and B is the width of the beam at the point under consideration. Now what you got to remember about shear stress, and this sort of makes it opposite of bending stress, shear stress is going to maximize itself at the neutral axis. And it will actually become zero at the outside edge. So that's completely reversed of the way that you saw it with bending stress, right? Bending stress was zero at the neutral axis and maximized itself at the outside edge. Okay? Shear stress is different. Shear stress is completely opposite. You know, maximizes itself at neutral axis and becomes zero at the edge. All right? Why I say width of the beam point under consideration is simply, you know, in this rectangular beam, the beam is always the same width. But you've already seen beams that have different widths, haven't you? You know, like a wide flange beam has a very narrow web, but its flanges are much wider. Okay, so it's not impossible that you'd have, you know, a case where a beam has one width on the top or the bottom and another width someplace else. All right? Let's get back to the static moment of area. The static moment of area, the book has a very good illustration of what it is. I refer you to that. But basically, what's going to happen is you're going to take the point where you're trying to get shear stress, and you're going to look at the area outside of it, either top, above, or below that point. You know, let's say above, since we're looking at the neutral axis. So it's the area outside that point. All right, times the distance from the neutral axis to the centroid of that shape. Okay, so wherever you're calculating shear stress at, look at the area outside of that point, okay? And then take that area and multiply it by the distance from the neutral axis to the centroid of that shape, of that area, okay? And again, it sounds harder than it actually is. So, let's show you this. Again, one thing I'd stress, when calculating this particular formula is, you know, watch your units. It won't be as bad for this as it, you know, or not as bad, but it won't be as tricky as it was with bending stress sometimes. But let's say, I mean, we'll just do, you know, I'll give you the shear. I'll say, hey, we got 50 kip shear force, and it's on a beam that's let's just say it's a 12 by 12 square beam. Okay? And you want shear stress at the neutral axis. Okay? So what would you do here? You got a shear force of 50 kips. That, again, is just given to you. Now, you know, again, you're going to be doing problems where you have to actually find what the shear force is, or maximum shear force. Your beam is just a 12 by 12 square. Neutral axis, of course, is in the centroid in the middle of that shape. Okay, so what are you going to do to calculate the shear force? What I do is I simply go through and list the four components. V, okay, Q, and here's the way Q works. I want shear stress at the neutral axis. So what's the area outside the neutral axis? It's this area, right? Well, how big is that area?
Maybe 6.
It's 6, right? Times 12. That's the area. And then you're supposed to multiply that area by the distance from the neutral axis to the centroid of that area. What's that distance? 3. So that's 72 times 3. It's 216 inches cubed. All right? Moment of inertia, again, it's a square. Square has the same formula for moment of inertia as a rectangle, 1/12 bh cubed. So base is 12, height is cubed, 12 cubed. So that makes this pretty easy, 1728 inches to the fourth. And what's your width of your beam at the point you want the shear stress taken? What's the width of the beam at the point you want shear stress? We want it at the neutral axis, so it's 12. All right? So our formula then becomes this. 50 kips times Q, which is 216 inches cubed, divided by I, which is 1728 inches to the fourth, divided by the width, 12 inches. So your shear stress on this comes out to be what? $50 times 216 divided by the product of 1728 times 12. What is it? .52. You got any units on that? Stress units, kips. You got inches cubed divided by inches to the fifth. So that's kips per square inch. 0.52 kips per square inch.